Hey everybody, let's give this problem a try. So we're trying to find the internal forces and moments as a function, and then have the shear and bending moment diagrams. So what's the first thing we do? Let's solve for the reactions at these supports. So there's the beam, we have x over here, y over here. So I'm going to decompose the reaction at this pin. I'm just going to call this A and B. So the reactions at pin A, I'll decompose. And then we have a roller at B. Okay, and then there is a distributed load here, which I can represent as a single discrete force. The magnitude is the area of the shape, so 1/2 base times height. Okay, and then the location of this force is at the centroid of the shape. So it's a triangle. So then over here, so 1/3 of the way over. So that means here to here is going to be 2 feet. Right? And then here to here is the rest of it. So here to, 6 feet over here, 4 feet over here. This is the middle. Okay, so now let's solve for those reactions. So in the x direction, AX, that's it. In the y direction, AY, BY minus 300. Some torque about anywhere we want. Let's say over here, A. Okay, so there's torque from BY, which is 12 feet, minus 10 feet, 300. Okay, so then let me point out the unknowns. Here, 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 here. AX is 0. Solve this for BY. 3,000 over 12. And then plug that value in right here. AY is 300 minus that. Okay, maybe I should punch it in the calculator. Actually, 3/12 is 1/4, right? So 1/4 of 1,000 is 250. And, there should be a 300, right? So 300 minus 250 is 50. These are pounds. Okay, and then AX was 0. Okay, so we have all three reactions. So now, if we draw the free body diagram, so we're done with this representation, right? Don't use this anymore. We just use that to find our reactions. Now we're done with it. Back to this representation here. Okay, so what do we have here? AX was 0, AY was 50, BY was 250. Okay, now if you cut the beam anywhere between here and here, between 0 and 6 feet, no matter where you cut it, between 0 and 6 feet, it's going to look like this, right? No matter where you cut it, the free body diagram will always look sort of like this. Okay. But then if you cut this diagram anywhere between 6 feet and 12 feet, somewhere over here, anywhere between here and here, then what will the free body diagrams look like? The left section will look like this. And the right section will look kind of like this. Okay. So then, right, and then this and this. How much was that again? 50 and 250. Okay. All right, so this particular problem, you have to do, or you have to make two different cuts, basically. So one between 0 and 6 feet over here, and then another one between 6 feet and 12 feet, right? And then now let's take a look. Which of these two sections would you prefer to analyze? Definitely feel like this one is less to deal with than this one. So I'm just gonna erase this. Okay, let's just focus on, and let me make a note that this is valid between 0 and 6. And then this one was only valid between 6 and 12. Okay, and now these two sections both look terrible. So I'm not sure if there's an advantage of one over the other. I'm just going to go with this one. I mean, they both look troublesome. So, okay, so now we can write 3 equations to solve for these 3 unknowns. Let's get started here. Okay, so x direction, we got this. That's it. Y direction, 50 minus v. Sum torque about anywhere we want. So I'm going to sum the torque about over here, the right end. There's no wrong choice. Okay, and then here to here was x, right? Because I'm cutting it at some arbitrary x. So the torque about the right end by this force would be in the negative direction. Okay, and then there's the couple. And here we go. So the axial force is 0. The shear is 50. The bending moment is 50x. And this is for x between 0 and 6 feet. Okay, now the rest of it. Okay, so now that we have this free body diagram, we can now represent it as a single discrete force at, let me label more of the dimensions here. Okay, so here to here is x, right? Because we cut it over here at x. Let me look at the picture. Okay, and then here to here is 6 feet, which means here to here is the leftovers, right? That's got to be x minus 6, because the overall dimension was 6. Oh no. X, sorry. Okay. All right, so now we can represent this as a single discrete force, which is the area of this shape. So now here's the question. How much is this vertical? Right, this triangle. How high is this? We know that here to here is x minus 6, and the original triangle, right, this was 6 and this was 100. So we know the slope is definitely 100 over 6, the slope of this. So as a function, let me go back to the original picture. You see this right here? Let me maybe extend it like this. What is this function? The slope is rise over run. So 100 over 6, x. But then the y-intercept is actually over here. So let me just write it like this, and then I'll let you check. When x equal to 6, look, this is 0, right? When x equals 0, 100 over 6 times negative 6 is over here, minus 100. When x equals 12, this is 100, which is over here. So this is the function. 100 over 6 times x minus 6 is the function. So that's what we have here. Let's see, it's getting... here to here, 100 over 6 times x minus 6. Okay. So if we want the area of that shape, I'll just draw the triangle again, right? 100 over 6 times x minus 6, and then here to here is x minus 6. What's the area of the shape? 1/2 base times height. Okay, there we go. I'll just leave it like that. Right? That's the area of the shape. Where's the centroid of the shape? Over here. 2/3 of the way over this way. Oh, sorry, 1/3 of the way over this way, 2/3 of the way over this way. So from here to here, that's 1/3 of x minus 6. Okay, all that to get this discrete force representation of our distributed load. Right, and then there's all the other stuff. There's axial force, shear, bending moment. Okay, so now that we have this free body diagram, let's solve. X, Y, some torque. Okay, x direction, P. Y direction, 50 minus V minus that. Let's see, can we simplify a little bit? So we got 100 over 12 times x minus 6 quantity squared. So it's simplified a little bit. Okay, and then is that everything in the y direction? Yes. Okay, some torque about wherever we want. How about this right end? Okay, so there's torque from this, which is negative 50 times x. And then there's torque from this, which is positive this much, 1/3 of x minus 6 times this force. 1/2 of, actually let me just write the simplified version. So that's 100 over 12 times x minus 6 quantity squared. Okay, so there we go. Oh, I forgot to write the couple from right here, the bending moment. All right, there we go. So now we got these three equations. So this is 0, solve for V. Move this on the other side, so 50 minus. Okay, and then here, just move M on the other side. Okay, let's see. So it's 50x, and then minus, let's see, 100 over 36, and then there's that cubed, right? Okay, so there we go. This is for x between 6 and 12. And then let me bring the other one. Okay, so here we go. That's it. That's the function, right? So so axial force is actually 0 everywhere. Shear looks like this. Bending moment looks like this. And then you don't need to know how to graph this in your head. You can just punch it on a calculator, something like that. Right? But generally, the shear will look like 50, and then that looks like, you see this is a parabola, but then there's a minus, so it's actually concave down, so it'll look something like this. And that, okay, and then at x equal to 12, then that's 6 squared, 36, so that's 50 minus 300. Okay. So that's 250. Oh, 50 minus 3, negative 250. So something like that. Not to scale, but, you know, something that looks like this kind of shape. This was, what was it again? 50, and this was, so not to scale, it should be, let me draw it again. So more like that. Okay, where this is 50 and this was negative, I already forgot, what 250 was it? Okay, and then bending moment looks like 50x, so kind of like that. And then at x equal to 6, that's up here at 300, right? And then for here now, at x equal to 6, that's 0 and that's 300, so then it's still over here. And then what does that look like? So a cube looks like this, right? Oh, I mean, like this. And then there's a minus sign, so it looks like this. So then it's some kind of, at x equal to 12, what do we have? 6 cubed over 36. So then that, I mean, you don't have to do it in your head, or you can just punch in the calculator. Okay, so that's 50 times 12, 600, and then that's 12 minus 6 is 6 cubed over 36. So that's 6 times 100, so 0, right? So it looks kind of like that. Okay, so, and again, you don't have to do it in your head. You could just use the calculator to graph it. The point is that if you look at the shear, you're like, okay, where's the shear? Like it's at 250, negative 250 over here, 50 over here. And then what about the bending moment? It hits a maximum right in the middle. The value is 300 foot-pounds. So that's important information as you make decisions as an engineer for your designs. Okay, so try and practice this problem. You can even try, I erased it, but you see how I picked the left section over here? You could have also tried the other section, which looks like, I'm going to say it looks like a composite of a triangle and a rectangle for the distributed load for the section. This is the left section, this is the right section. All right, so you could also try this as practice. Use this free body diagram, and you should get literally the exact same answer here. Okay, so give it a try. It's a little bit complicated, so it takes practice. So let me know if you have questions. I'll see you in the next video.